This is Jack Jackson with part 9 of a series of lectures on discrete probability. This is on combinatorics. Combinatorics is the theory of counting. So we're going to be learning certain counting techniques today. So recall that probability, at least in the case where the sample space is finite, is very simple. All we have to do is just count up the size of the event and divide it by the size of the sample space to find the probability of that event. Sounds pretty simple. In fact, the concept is very simple. However, counting, not quite so easy. Probability easy, counting, not so much sometimes. So we've already seen that counting the sizes of some of the events in sample spaces can be difficult. So we're going to learn some special techniques that will be helpful in certain examples. So the study of these special techniques of counting in these more complicated situations is called combinatorics. In this lecture, we're going to study 6 different combinatoric techniques for counting certain situations that will show up sometimes in certain probability computations. And this lecture will be just on the counting techniques, however. So let's look at an example here to start with. Suppose there are 4 people with last names starting with the letters A, B, C, and D. How many different single file lines can we make with these 4 people? See if you can figure that out. Go ahead and do that now. Press pause. Well, you're back. Did you think of making a tree? Well, that would be a good thing to do, to go ahead and do this. If you didn't, you might want to try to press pause and make a tree now. If you have, let's go on. Alright, here's a tree that shows all the different combinations. Now, from our initial root vertex there, we go out and make our first choice, and we have a choice of either A, B, C, or D for the first person in line. But notice that once we choose the first person, let's say we chose person A cannot be the second, third, or fourth person in line. So we only have 3 choices now for the second person in line once we've chosen the first person. So if we, for example, if we choose A for the first person, we can either choose B, C, or D for the second person. Likewise, if we would choose B, our choices for the second person are A, C, or D, and so forth. Now, so for each of the 4 branches we start with, each one of those has 3 possibilities for the second choice. Okay, so for each choice of first and second, then now we're down to only 2 choices for the third person. So for example, if we choose B and then C, we can only do A or D for the third person. And once the first 3 are chosen, we really only have the 1 choice left for the fourth person because they're completely determined. There's only 1 person left. So, let's look back at this tree. Notice because the first choice we have 4. Because every one of those we have 3, and every one of those we have, for every one of those choices we have 2 for the next, and every one of those just 1 for the next. We can multiply to see the total number. We can take 4 times 3 times 2 times 1. And that's going to give us the total number. So the total number is 4 choices for the second, for each one of those 3 for the next, for each one of those 2 for the next, and for each one of those 1 for the next. That gives us 4 times 3 times 2 times 1, which is 24 different possibilities. And if you go back and count those in the tree, you'll see that that's exactly what we got is 24. Okay, you do this one. Suppose there are 8 different books, and we're going to just put them in a shelf on a sort of the standard way you put them on a shelf. How many different orders can we place these on that shelf? Go ahead and figure this out. Press pause now. Well, did you think of a tree again? This one is a pretty big tree, so we might not want to actually draw it out, but do you think about it, we should have 8 choices for the first branch, from the initial choice for the first book. And for each choice we pick for the first book, there's now going to be 7 choices for the next, because we can't repeat the first book. And then 6 choices for the next, 5, 4, 3, 2, and 1 for each successive one like that. And when you do the tree, again, I'm not going to draw it out because it's a huge tree. But you can see the basic idea that you're going to get 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 40,320 different ways. Wow! Look how huge that is. And this is amazing how fast this grows. You're going to find out in this lecture that these combinatorial techniques that we're going to be using, we're going to be counting things that get very large very quickly. So that leads us to the following definition of the factorial function. N factorial is defined to be, well, we have a special case first of all. It's useful for us to call 0 factorial 1. And that's just kind of a weird one that's off by itself, but it's useful. We can also think of that, if you have 0 objects, how many ways can you put them in order? Well, there's just one way. There's no objects to arrange. So that's just 1. And so it's useful for us to think of 0 factorial as being 1. So we define it that way. So that's in a case by itself. But for any natural number, then we can use the basic setup that we just did. We take n factorial, and by the way, the notation is n exclamation point. That's not an excited n. It's just the notation we use for this particular function. So n factorial is the product from k equals 1 to n of k. Now you see that capital letter pi. Of course, lowercase pi is a specific number. It's the circumference of a circle divided by its diameter. But capital pi is a lot like the capital sigma. Remember, we use capital sigma for summation notation, which meant basically add them up. And capital pi is product notation for basically multiply them out. So when we're saying the product from k equals 1 to n, we're substituting 1 in place of k, and then 2 in place of k, and 3, and so forth, all the way up to n, and then we're multiplying those together. So what that is 1 times 2 times 3 times 4 times 5, all the way up to whatever n is. And if you think about it, that's backwards from the way we did our tree and did our example, but of course multiplication is commutative. We could write it backwards or forwards, it doesn't matter. And we get the same answer, and this is exactly the way that we need to count the number of ways of permuting, that is, placing in order, in distinct objects. So that the number of ways of permuting or placing in order in distinct objects is n factorial. So now we have the first of our techniques we're going to be studying today. Now let's look at another situation. We'll see if this is the same or if this is a little different. Suppose there's an organization with 25 members, and the organization wants to select a slate of 4 officers. Let's say they got to make a president, a vice president, a secretary, and a treasurer. So here are the rules. There will be a single individual chosen for each office. So no co-officers. There's no co-president or co-secretary. Okay? But a person is allowed to hold more than one office. So for example, we could get the same person to be secretary and treasurer. How many different slates of officers are possible? Go ahead and see if you can figure this out now. Please press pause. Well, again, you could think of making a tree. I don't want to actually draw it out. But think about what it would look like. You would have 25 choices for the president, and for each one of these there would again be 25 choices for the vice president, because any one of the 25 members, including the one that was chosen for president, could be chosen for VP. And then how about secretary? Well, for each one of the choices of president and vice president, there are 25 additional choices for secretary, and then once those are picked, there are 25 more for treasurer. So if you visualize the tree, you got your root and vertex going out to 25 choices for president. Each one of those goes to 25 choices for vice president. Each one of those goes to 25 choices for secretary, and each one of those goes to 25 choices for treasurer. So since they're all the same and each one's going out, we can just multiply. So that's 25 times 25 times 25 times 25, or 25 to the 4th power. That turns out to be 390,625. Wow. That's how many different slates of officers are possible. It's amazing that it turns out to be that big, but that's what it does. Lots of different ways of doing this. Okay, so can you see a sort of a general thing here? Notice that one way we could choose these officers, probably not the best way for this particular organization, but one way we could do it is we could put all of the names in of all the people in the organization, all 25 names on pieces of paper, put them in a hat, shake them up, and just randomly draw one out for the president. Once that's done, we put the name back in, mix them back up, and draw a name for the vice president. Once that's done, we put it back, mix them up, draw one for the secretary, and so forth for the treasurer. So notice each time we're replacing the names when we choose them, and that allows us to have repeats. So this repeats allowed is sometimes called with replacement, even if they're not actually chosen that way. Okay, so repeats allowed with replacement is basically the same thing. And notice the order does matter here. Selecting Bob as president and Joan as vice president is different than selecting Joan as president and Bob as vice president. The order is going to make a difference there because the offices are distinct. They have differences in the offices and their duties. So here's what we have. We're going to count something here. We're counting an ordered list of choosing K objects from a set of N distinct objects. So N was the number of people we're choosing from in the last example, and K was the number of offices. The repeats are allowed. Order matters. Repeats are allowed. Another way to say that's with replacement. And so the number of choices is just N to the power K. So another technique down. So try to work this problem. Is this the same as something we've seen already, or is this something new? Suppose that there is an organization with 38 members. The organization places the names of all the people in a hat and draws for a prize of $500. The name is returned to the hat, and the name is drawn for a $200 prize. That name is again returned, replaced there, and you mix them up and draw the third prize of $100. In how many ways can the prizes be distributed? Please figure this out. Press pause now. Well, this is exactly like the last example that we just did. It's going to use this power rule. Notice that we're choosing K equals 3 items from a group of N equals 38 items, people in this case. The order matters. It's done with replacement, so repeats are allowed. So this is just a power rule. 38 choices for the first prize. Each one of those, there's 38 for the second, and each one of those combinations, there's 38 for the third. So we're just multiplying those together, or we're using our power rule. 38 to the third power, that's N to the K. And that's 54,872 different ways the prizes may be distributed. And of course, this is a real easy computation on a TI-84 calculator. You just do 38 to the power 3, one of our basic operations, and you can see a screenshot there. Okay, let's look at this example. Is this the same as something we've already done, or is it slightly different? If it's different, how do we modify our answer? Suppose there's an organization with 25 members, and again they're selecting 4 officers, a president, vice president, secretary, and treasurer. Again, there will be a single individual chosen for each office, so no co-officers. But this time a person is not allowed to hold more than one office. If you're secretary, you can't be any one of the other 3 offices. How many slates of officers are possible in this case? Is it the same as the officer situation before? It's still 25 members, it's still 4 officers. But this time we're not allowing you to hold more than one office. So is this going to be a larger or smaller or the same number that we got when we did allow people to hold more than one office? See if you can go ahead and figure out how many this would be. Press pause now. Well, again we consider a tree without actually drawing it out. Notice that, once again as before, it starts with 25 choices for president. But this time each one of those only has 24 choices for vice president. And of each of those pairs of president-vice president, we're going to get 23 choices for secretary. And each one of those triples, we're going to get 22 choices for treasurer. So we're going to end up multiplying not 25 times 25 times 25 times 25, which is what happened when we did allow repeats, But this time, since we don't allow repeats, it goes down each time. So it's 25 times 24 times 23 times 22, which is 303,600 different slates of officers possible. Notice we started with 25, which is how many members we had, and we have a total of 4 factors, which is how many officers that we're picking, and the numbers went down 1 each time. Okay. Now, another way of writing this, perhaps a more complicated way, you might argue, and I might agree with you, but we could take 25 times 24 times 23 times 22 and multiply top and bottom by 21 factorial and make that a fraction. And then the top is 25 times 24 times 23 times 22, and the 21 factorial has 21 times 20 times 19 times 18, all the way down to 1. And so the numerator is just 25 factorial, and the denominator is 21 factorial. 21 factorial is 25 minus 4 factorial. And now you can see that this is n factorial over n minus k factorial. So this is one way to write what we just figured out, using the factorial thing that we've already defined, the factorial function. So this is what we call a permutation. So what we're doing here is choosing from a set of indistinct objects. We're choosing an ordered list of k of these objects. Repeats are not allowed. It's done without replacement. And so the number of choices is, we call this n permute k. We'll normally use this notation, subscript n, p, subscript k. And that's n factorial over n minus k factorial that we just saw on the previous slide. And of course we also saw earlier that what you do is you start with n, and then you multiply by n minus 1, and then you do n minus 2, and you keep doing this till you have a total of k factors. The last one will be n minus, parentheses, k minus 1. So what we're doing is we're doing a product from I equals 0 to k minus 1 of n minus I. Okay, this is called a permutation, and there's different notations I've seen for this, maybe even some more besides this, but the one on the left there, n, subscript n, p, subscript k, is what you'll see. Sometimes you'll see both of those n and k's on the right side there. N is a superscript, k is a subscript. Sometimes you'll see them in parentheses like p of n and k, like function notation. And sometimes there might be some other notations, but these are the ones that are most common. We're going to probably use the one on the left because this is in your calculator, and we're going to use that in our calculator in a little bit. Now suppose there's an organization with 57 members. This organization wants to select a slate of 8 distinct officers. There will be a single individual chosen for each office, no co-officers. But a person is not allowed to hold more than one office. How many slates of officers are possible? Figure this one out now. Press pause. Okay. Well, let's see what we have here. Again, this is exactly the setup for our permutations that we said. We're choosing k equals 8 officers from a set of n equals 54 distinct people. Order matters, since the offices are different. It's done without replacement, so no repeats are allowed. And so how do we do this? Well, you can see the computations here on the right. That's npk, that is 57 permute 8, which is the way I would read that. So that's 57 factorial over 57 minus 8 factorial. Or you start at 57, choices for the first one, then times 56 for the second one, times 55, and you work your way down to 50. If you count those factors, there are 8 factors there. And if you multiply all those out, I used a TI-89 calculator for this, so that it would show me all the digits, and it turns out to be 66,625,230,672,000 different ways, or approximately 6.6625 times 10 to the 13th. Now, there's a shortcut for this built into your calculator. The factorial is built in, the permutation and the combination that we're going to see here in a little bit are all built in. They're found kind of the same place. So what we do is we type in, well, down here are the exact keystrokes you can see down here with these little key graphics down here. So you push the 5 button, the 7 button, that gets you your 57. Then you push math, and left arrow will take you from where it says math here. Left arrow will take you over and highlight PRB, which is probability. And we see, for example, if we want to do 57 factorial at this point, we would just push factorial, and that would give us 57 factorial. In this case, we want NPR, and so we do number 2, NPR, and then we type in 8, and then enter. And it gives us that. Didn't quite give us that very last digit, but it does give us everything else, so it rounds it off a little bit. 6.662523E067. Then you got this E13. That E13 means times 10 to the 13th power. This number got so big it went into scientific notation for us. Okay, and I've got it written above in standard notation. Like I said, I used a different calculator to actually figure out that it's actually a 2000 for those last 4 digits. Notice that the calculator calls this NPR rather than NPK. It really doesn't matter what letters we use there. I prefer when I'm writing it down to call it NPK because, especially if I'm writing these by hand, sometimes an R looks a little bit like an N. And it can get a little confusing. A K is pretty distinct from an N, so I use NPK. But NPK or NPR doesn't matter. Same thing. Same notation. Alright, so now we have that's pretty cool that we've got that built in the calculator because it will go ahead and figure out these numbers for us. So that's called a permutation. Order matters, no replacements. Without replacement, no repeats. Now let's try to do this example. So again we have our organization with 25 members, and once again we're selecting 4, but this time they're going to just form a committee. How many different committees are possible? Is this the same as before or different? What's different about this? Well, one of the things that's different is the order doesn't matter. Remember before, say if we have Bob as president and Alice as vice president, that's different than Alice president, Bob vice president. Okay? But if we have a committee and we pick Bob and put him on up first and then Alice second, or we put Alice on it first and then Bob second, doesn't make any difference. So still the same committee. There's no distinction among the jobs of the people on the committee. Right now we're not talking about any kind of chair of the committee or anything like that. They're all just equal members. So this time the order doesn't really matter. So is this going to be more or less than the last one? Should be fewer different possibilities, because we could just figure out how many we got when we did permutations to figure out how many would be there in the committee if the order did matter, but then we have to somehow figure out the fact that we've counted them more than once. See if you can figure out what this would be. Press pause now. Okay, this is a little harder, but let's see if we can figure this out. Well, if the order did matter, that would be just 25 permute 4. That's 25 times 24 times 23 times 22, or 303,600 ways, just like we did when we had 4 officers. But the point is, now we've counted the same group of 4 people many times. How many times? Well, it's exactly the same way we can put those 4 people in order. In every group of 4 people, again, we've counted them that many times. So we need to divide this out. Divide this number by the number of ways of taking 4 people and put them in order. Well, we already know how to do that. That's just 4 factorial. So we want to take our 25 times 24 times 23 times 22 and just divide it by 4 times 3 times 2 times 1. Now look, 4 times 3 times 2 times 1 is 24, so that just cancels the 24 out in the top, and what we're left with is 25 times 23 times 22. Go ahead and multiply those out, and I think you'll find that's 12,650 ways. So if the order mattered, like the 4 officers, that was 303,600 ways. But if the order doesn't matter, like a committee, there's only 12,650 ways. So again, if the order matters, think officers as your canonical example. And if the order doesn't matter, think committees. That would be a good example to think of there. So look what we have here. We have another way to write it with the factorials. We've got our, just as we have with our permutations, 25 permute 4 was 25 factorial over 25 minus 4 factorial. Same thing for combinations down here, but we also divide by 4 factorial. And we call that 25 choose 4, and that's 25 C4 instead of 25 P4. So the general technique here, again, is now we're counting choices. This is an unordered set of K objects that we're selecting. So order doesn't matter. And we're again selecting from indistinct objects. Again, repeats are not allowed, so it's done without replacement. And the number of choices is N choose K, subscript N, C, subscript K. That is defined to be N factorial over N minus K factorial times K factorial at the bottom. Or in other words, that's N pk, N permute K, divided by K factorial. Now there's several, this thing here is called either a combination or it's often called a binomial coefficient. And it's sometimes denoted as NCK, the way on the left there. That's the calculator notation. That's the notation I'm going to use in this class. But you often see some of these other notations, particularly the one on the right is a very common, perhaps the most common notation for this. It's an N over a K, no fraction line or anything like that, just an N over a K in parentheses. And that's called a binomial coefficient or a combination. So be comfortable with these notations, particularly the one on the right and the one on the left. Be sure that you understand both of those notations, so if you see either one, maybe in your book or your homework or test or whatever, you'd be able to use either one. Most of the time I'm going to use the one on the left. Your book might use the one on the right, so be careful that you could use either one. By the way, these are called, there's some very interesting things about these binomial coefficients. They're used as coefficients when you're expanding a binomial to a power, and they're also the same numbers in Pascal's triangle if you've seen that before. If you haven't, that's not really important for us right now. Let's move on. Suppose we are randomly drawing a hand of 5 cards from a standard deck. How many such hands are possible? So shuffle up the cards really good, randomly draw off the first 5 cards, and look at them. How many different ways, different hands can we get? For example, a game of poker is done this way, where you draw 5 cards. So how many different poker hands are there? See if you can figure that out now. Please press pause. Well, let's think about this. This is exactly the same situation we were in last time, where we're drawing, we're not replacing the cards. We're drawing from a set of N equals 52 distinct objects. We're pulling from that K equals 5 objects. We're not repeating, but the order doesn't matter. Once you've got the 5 objects, you can rearrange them in your hand however you want. So, that is our 52 choose 5. There it is, 52 factorial over 52 minus 5 factorial times 5 factorial. In other words, the top is the first 5 numbers, starting with 52, coming down, 52, 51, 50, 49, 48, all multiplied together. And that's your permutation part, and then we want to divide that out by the ways of ordering, of switching the cards in the hand, 5 times 4 times 3 times 2 times 1 in the denominator. Now, by the way, let's do some canceling here. In the bottom, we have 2 times 5 is 10. Cancel that with the 50 in the top, and that knocks the 50 down to a 5. 4 times 3 is 12. That goes into 48 4 times, so it knocks the 48 down to a 4. So what we're left with is 52 times 51 times 5 times 49 times 4, which is 2,598,960 ways. It's kind of an interesting thing that both the permutation and the combination, when we do this, always turns out to cancel out to be a whole number, which of course it should be. Once again, we can use our calculator. Just push these numbers, these keys in this order. 5, 2, which gets you your 52. Press the math button and left arrow, which will get you our probability, PRB. And then number 3 is our choice for NCR, so just press 3 to get NCR. And then, of course, 5, press that to get the 5. And then enter, and you'll see that number computed, and you can see the screen for it right there on the right. So you should practice this with your calculator. Again, we have under this math probability, we have the factorial, the n-choose-r, and your NPR. And so you have shortcuts for all 3 of those basic techniques. In fact, all 3 that we've learned, and except for what we've learned 4, we also learned the power, but that's just right on the front of your calculator. Now, let's look at another one to sort of complete this. We've looked at an example where the order matters and we do it without replacement. We looked at where the order matters, we do it with replacement. Order matters with replacement, order matters without replacement. We've done order doesn't matter without replacement. What if we do order doesn't matter and you do it with replacement? In other words, we allow repeats. So let's kind of finish this out for this nice little group of 4. So suppose you're placing a food order for a group of 8 people at a fast food restaurant. Now they got to choose one of 4 meals. So either this restaurant only does that or we're only allowing them to do that. So they can choose a number 1 meal, a number 2 special, a number 3 special, or a number 4 special. So they have to choose one of those things. No special orders. Now notice when you go up to the drive-thru, the people at the drive-thru don't need to know who gets which meal. You can sort that out when you get back, bringing the food back. So all you have to do, so they don't care what order, you don't care what order they hand them out of the window. They don't care who gets what. You'll sort that out later. All you care about is that you get the right number of number 1s, number 2s, and number 3s. So you'll just go up to the window and say, okay, I want, say, 3 number 1s and 2 number 2s and so forth. Okay? So how many different ways can we do this? See if you can think about that a second. Alright, well this one's a little challenging. So let me show you a way of doing this that might help us figure this out. Okay, one way we can do this is we've got 8 different meals that we're choosing. Okay, so that's the K objects. And we're selecting from n equals 4. Notice in all the other examples, n was bigger than k. But here, k could be the same, smaller, or even bigger than n because we're allowing us to repeat here. So we're choosing k objects, k equals 8 objects from a set of 4, n equals 4. The order doesn't matter, and repeats are allowed. So one way to represent this is we want to place a bunch of little blanks down there. And we're going to take a blank for every one of the objects that we're selecting, the K objects, meals that we're selecting. And then we want a divider, and we want n-1 dividers. So n-1 in this case is 3. So we're going to put 8 plus 4 minus 1, or 8 plus 3 is 11. So we're going to put down 11 blanks. And then we're going to place 3 dividers, just 3 little vertical lines, somewhere on these blanks. And when we do this, this is going to allow us one way of representing how many meals of each type. So for example, you see something work down here where I've got blank, blank, divider, blank, 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 divider, divider, blank, blank, blank. So 3 of the 11 blanks have been filled. And then you've actually got 8 actual blanks. with nothing in them. And so what we do is we count the number of actual empty blanks to the left of the first divider, and that's how many number 1 meals. And then how many between divider 1 and divider 2 will tell you how many number 2 meals. How many between divider 3 and 4, 2 and 3 will tell you number 3 meals, and how many blanks to the right of the last divider will tell you how many number 4 meals. So for example, this one that I have listed here has 2 blanks to the left here for 2 number 1 meals, then a divider. 3 blanks in a row here between these 2 dividers, so that's 3 number 2 meals. There's nothing in between these dividers, so that means there's no number 3 meals. And then 3 blanks on the right will be 3 number 4 meals. Okay, so if you think about this, this is one way we could represent every single possibility is by just moving these around. So what we're now doing is we've got 11 blanks, and out of the 11 slots, and we want to distribute the 3 dividers among them. How many ways can we put that? Well, it doesn't matter if we switch 2 dividers. So what we're doing is we're choosing 3 slots out of 11 where the order doesn't matter. That's a combination again, or binomial coefficient. Or we could think of, instead of choosing the dividers, we could think of choosing the empty slots, the 8 empty slots. So we're choosing 8 empty slots from a total of 11 blanks. So now, with that information, go ahead and figure out how many possibilities we have. Press pause now. Well, did we get this? It should be 8 plus 4 minus 1 is 11. And we're choosing from that 3, 4 minus 1, 3. And so that's 11, choose 3, which is 11 factorial over 8 factorial, 3 factorial. But now notice it's also in the bottom, whether we have 8 factorial, or then 3 factorial, 3 factorial, then 8, it doesn't matter. And that's also exactly 11 choose 8. So notice that 11 choose 3 and 11 choose 8 exactly the same amount. And that's 165 ways, which you can do that on your calculator, for example. And you might check that out. Do 11 choose 3 and 11 choose 8 on your calculator, both, and you'll see that you get 165. Go ahead and check that now. Alright, so let's do this in general. So if we're counting choices, again, it's an unordered set of k objects, and they're in distinct objects to choose from. This time we are allowing repeats, so it's with replacement. The number of choices of these lists is the same as distributing k blanks among n plus k minus 1 positions, or equivalently distributing n minus 1 dividers among n plus k minus 1 positions. So that is n plus k minus 1 choose k, or n plus k minus 1 choose n minus 1. Either way you want to think of that. Alright, 5 techniques down, just one more to go. In this last one, we're going to look at this example. How many distinguishable ways can we place the letters of the word abracadabra in order? So here we have, well, let's count the letters. Did you get 11? So we have 11 letters. Now, if all the letters could be told apart, there would be 11 factorial ways of putting those in order. However, some of these would look the same. For example, I could take this specific order. If I switch the first letter and the 4th letter, it's going to be the same thing. You can't tell it apart because you just switched an A for another A. In fact, I could take any of those A's and move them around and just swap them for another A. You're not going to be able to tell anything happened. And yet I'm counting all those things as different things when I do the 11 factorial. So how do I fix this? How do I adjust for the fact that we could swap those A's around? And how about the B's and the other letters? See if you can figure this out. Press pause now. Well, let's take a look at it now. Let's count them up. we have 11 letters. There are 11 factorial ways of placing those letters in order, but we can't tell some of them apart. They're not indistinguishable. They're not distinguishable. Some of them are indistinguishable. So if you look at it, we count them up by letter. There are 5 A's, 2 B's, 1 C, 1 D, and 2 R's for a total of 11 letters. So we could start with our 11 factorial ways of putting them in order, but we could switch those A's around, and there are 5 of those A's. There are actually 5 factorial ways of switching those A's around. Okay? So what we have to do is divide that by 5 factorial. Similarly, we can switch the 2 B's if we want, so there are 2 factorial ways of doing that. Only one way, you can't switch the C or the D, so that's just one. But the R, there's 2 ways we can write that. That's 2 factorial. So what we end up doing, one way we can do it is write it this way. It's 11 factorial, divide by the 5 factorial, divide by 2 factorial. If we want, we could write divide by 1 factorial and 1 factorial and then 2 factorial. And if you do that, you get 83,160. Of course, the 1 factorials are just 1, so you could leave them out. 2 factorials are just 2, so you could leave off the factorials there. Of course, 5 factorial is 120. But we can work that out. Now, so this is a general situation. We have n objects altogether, but they are of some various different types. Okay, type 1, there are n sub 1 of those. Type 2, there are n sub 2 of those. And type 3, n sub 3, and so forth, up to the kth one, there's n sub k of those. And if we add up all those n sub whatevers, n sub 1, n sub 2, n sub 3, up to n sub k, then we get the total number of objects, which is n. Then the way number of ways of placing those in order that we can tell the number of, that should say distinguishable, not indistinguishable ways, the number of distinguishable ways of putting these objects together, some of which are indistinguishable, is given by n factorial over the product from j equals 1 to k of n sub j factorial. So it's, in other words, n factorial, then n1 factorial, n2 factorial, and so forth. And if you look back, that's exactly what we had on this abracadabra thing. So we had 11 factorial ways at the top, and then we take how many we've got of each one, just stick a factorial on each one of those, multiply them together, that's the denominator, divide out, you've got your answer. And that's what this formula here is saying. So let's summarize. There are 6 things that we have looked at. One is this one here. What are we doing here? We're taking a group of things that are, some of which are the same, and we're putting them in order. And how many different ways can we figure that out? And that's given by this formula here. We have this one at the top, the number of ways of permuting or ordering a set of n distinct objects. They're all different this time, and we want to put them all in order and use all of them. That's n factorial. And then we have this chart here. N is the number of items that we're going to choose from. K is the number of items that we're choosing. Then we have basically 2 conditions. Does the order matter or not? And do we repeat or not? And that gives us 4 different possibilities. Okay? So notice that we're doing it without replacement. The k needs to be less than or equal to n. N and k are 0 or positive numbers. K and n are whole numbers. When we repeat, we allow repeats. K and n can be any whole numbers. 0, 1, 2, 3, 4, etc. So, look what we have here. The first one we did was this lower left. Repetition was permitted, but the order mattered. That was n to the k power. Then the next one we did was above that, upper left. That was the order matters and repetition not allowed. That was n permute k. And you'll see that there. That's n factorial over n minus k factorial. And then we went to the upper right next. Again, the order, this time the order does not matter, and repetition was not allowed. That's n choose k. And then finally we have one more, and that's the lower right, where the order does not matter and repetition is allowed. That is the one in the lower right there. So let's remember our examples. When we go back to here, this example, think about abracadabra, putting the letters in order. Think about these examples when you have problems. The lower right, lower left there, n to the k power, that was where we had officers, and you could repeat. Permutation, permute k, think of officers, no repeats. So the order matters. Upper right, think committees. So you have order doesn't matter, no repeats. And finally at the bottom, think of placing your orders at the drive-through. Order doesn't matter, repeats allowed. And if you think of these examples, that will help see. In another example, it may be different. It should be kind of like one of those examples. And so now we have 6 different combinatorial techniques that can help us count things, which will also help lead us to probabilities in counting events and sample spaces.